So hello, everyone. I'm going to be talking today about sum-extensivity. So what is this? It's generalization of the concept of extensivity to context of monoidal structures called sum structures. And I want to mention that the work that I'm presenting over here includes contributions from NITheCS, Michael Hoefnagel, Zera Bianalitza, and myself. So we're all part of this project. Okay, so we're just going to cover some preliminaries, and our journey is going to start with cover relations. So this is a notion introduced by Zera Bianalitza in 2009. What is a cover relation? Well, it's a binary relation on the class of morphisms of a category, satisfying the following. So in order for a morphism G to cover a morphism F, they need to have the same codomain. And we need this left preservation property satisfied. So if G covers F, then HG covers HF for any H, composable. And we need to have this right preservation property satisfied. So if G covers F, then G covers FE for any E composable with F like this. Okay, cool. So a simple example of a cover relation, if we take our category to be the category of sets, and we say that like G covers F whenever the image of G contains the image of F as a set. So this is like quite a natural example of covering. And this is kind of the picture we have over here. So if we require even further that like we have inclusions of sets into one another, then we like actually get covering subsets, or covering sets. Okay, cool. So on to some structures. We impose some axioms on cover relations. So the first axiom is as follows. So if I have any objects x and y, then I can consider all diagrams of the following form over x and y. So that's like a morphism G with domain y and a morphism F with domain x, where G covers F. So if I consider all diagrams of that form, I need to have a diagram initial among them. So that's like a diagram with a unique morphism from its middle to C, any C, making the triangles commute. Okay, and we label this initial diagram as follows. So the C we take to be x plus y, and our two morphisms we take to be inclusions. We label as inclusions. Okay, then we also require this a star axiom. So here, just if we have any diagram of the following form, then the right leg of this diagram covers F, if and only if G covers the left leg of this diagram. And it turns out that this corresponds to sort of associativity condition. So we're going to get some monoidal structures out of this thing in a bit. Okay, and then we also require that the unique morphism from the initial object covers and is covered by every morphism in your category, and we denote this with exclamation point. Okay, so it turns out that there's a one-to-one correspondence between bi-cover relations, so those are like where the inverse is also a cover relation, satisfying these three conditions, and monoidal structures on C, satisfying the following. So the initial object needs to be our monoidal unit, or our monoidal unit needs to be initial. And we need to have that for any objects x and y. If I take like the sum of the identity on x and the initial morphism to y, and I take the sum of the initial morphism to x and the identity on y, I get this pair of morphisms. I require that this pair is jointly epimorphic. Okay, and if those two conditions hold, I have a sum structure. So my monoidal structure, I call a sum structure, and we have the following notation. So if I just like append the right and left uniters onto these morphisms that are required to be jointly epimorphic, then we label these as inclusions to our sum. Okay, so how does this one-to-one correspondence work? So given a monoidal structure or given a sum structure, we can associate a cover relation to it as follows. So for any morphisms F and G, we have that F covers G if and only if there exists this morphism from the sum of their domains, making this diagram commute. And if this morphism does exist, then it needs to be unique, since they're jointly epimorphic, since our inclusions are jointly epimorphic. Okay, and if the indiscrete cover relations, that's like where everything with common codomain is related, satisfies condition I, then the associated sum structure is a coproduct on this one-to-one correspondence. So we can see that like sum structures are a sort of generalization of coproduct, where we don't necessarily require existence in the universal property, but we do require uniqueness. Okay, and then one last concept is that of C-reflecting morphisms. So the definition is quite simple. We just have that like a morphism H is C-reflecting if and then if HG covers HF implies that G covers F. So pictorially, what do we have going on here? So if we have that there exists this morphism from the sum of the domains making these long triangles commute over here, then there needs to exist a morphism from the sum of the domains to common codomain of F and G, making these triangles commute for any morphisms F and G. Then we have that H is C-reflecting. Okay, an example of sum structures is the weakly unital structure on groups. So here on objects, we just take the sum of objects to be the product of two groups, and we take our inclusions to be that induced by the identity morphism and the zero morphism for each of our summons. And it turns out that this forms a sum structure. Okay, and here we have that G covers F if and only if their images commute in their common codomain. Okay, cool. So the other part of this project is extensivity. So extensivity was introduced by Cogboni, and Walters in 1993. And here's one formulation of the condition. So if a category has coproduct, then we say that it's extensive if for any two objects, x1 and x2, we have that the canonical functor induced by our coproduct that goes from the common category over x1 times the common category over x2 to the common category over their sum is an equivalence of categories. So just pictorially, what does this canonical functor do? So on objects, it would take like a morphism to x1 and a morphism to x2, so a pair, and then send that to the morphism induced between the sum of the domains and codomains. Okay, cool. So a theorem in the same paper where they introduced this notion is as follows. So we have that a category satisfies that condition if and only if it has pullbacks along some inclusions, so it has coproducts, and for every commutative diagram of this form, we have that the top row is a coproduct if and only if the left and right squares are pullbacks. Okay. Nope, that's the wrong way. Cool. So the canonical example of an extensive category is category of sets. And so this we use for all of our intuition of extensivity. So just a quick motivation for why that would be the case. So if I have any commutative diagram of this form, then I have that my two squares are pullbacks, if and only if A1 and A2 are the inverse image of x1 and x2 along F, respectively. And we have that holds if and only if this top row over here is a coproduct. Okay, just for a quick motivation. We have some other examples of extensive categories. So extensive categories are usually geometric in flavor, and categories that are usually geometric in flavor also tend to be extensive. So the list of extensive categories is quite extensive. So some examples, we have categories of graphs, so like simple graphs or directed graphs, etc. And then any elementary topos, I believe, is extensive. We have the category of affine schemes is extensive, so maybe that's like a surprising one if you haven't seen it before. And then the category of topological spaces is also extensive. Okay, also maybe it's worthwhile to think about things that are not extensive. So the algebraic categories tend not to be extensive. So for example, the category of groups is not extensive, and maybe if you'd like an example for why that's not the case, if we take like A to be the integers, and then like x1 and x2 to be the integers, then you're going to have like, these are abelians, so you can have like the product of x, z and z down here. Maybe we can take like the diagonal morphism to be our f, then the pullback is going to be trivial on either side, and we're not going to have that like my two A1 and A2 is going to sum to give me the integers again. Okay, I should have drawn a picture for that one maybe. And then the category of commutative rings is also not extensive, but it's coextensive because affine schemes is extensive. Okay, so the other, well, one of the goals of this project was to sort of look at standard results for extensivity and generalize them to the context of sum structures. So I will summarize these results for you. So first off, we start by defining what disjoint coproducts are. So if we have a category with coproducts and pullbacks along some inclusions, we say that coproducts are disjoint if inclusions are monic, and we have that pullback of inclusions are initial. So I realize here that like these are actually the same diagram. I could have just drawn one. But yeah, so the pullback of one inclusion along another gives us the initial object. Okay, now it turns out that in any extensive category, coproducts are always disjoint. Okay, an initial object we say is strict if any arrow into it is an isomorphism. And it turns out that in an extensive category, initial objects are always strict. And then we say that a coproduct diagram, maybe of this form, is universal if putting it back along any morphism F into the sum in the middle gives us a coproduct diagram upstairs. So another way of thinking of this is maybe like if I have an F coming into my coproduct over here, putting F back along each of the inclusions gives us a coproduct upstairs as well. So that's like half of the extensivity condition. Okay, and then it turns out that a category with finite products, coproducts, and pullbacks along coproduct inclusions is extensive if and only if coproducts are universal and disjoint. So this is quite a nice theorem. It sort of gives us an alternative characterization of extensive categories, and it also like tells us that coproducts are well behaved if we consider well behaved to mean behaving like disjoint union of sets. And maybe another reason why this is nice is because I think like this condition of coproducts being universal and disjoint is almost like some of the Girard axioms for a Grothendieck topos. So I think there you need like co-limits to be universal. But yeah, so it tells us that like an essential part of being a Grothendieck topos is being extensive, which is nice.
So you're saying something I didn't know. So you're saying that being a topos is like extensivity for colimits?
I mean, there's like a number of other axioms that I think a Grothendieck topos needs to satisfy. Okay. But yeah, so we need universality for all colimits, not just coproducts. But we only need disjointness for coproducts.
Okay, so you're not saying what I said, right?
Okay, maybe there's something to look at there. To what extent?
There's a result not for toposes, but for infinity toposes. That is precisely this extensivity thing with arbitrary codoms, but you can't do it in a one category. So you can but for infinity topos, there's an axiom that says that.
Okay. But yet it's still one of the axioms, it's not.
I think there are two axioms, and that's one of them.
Okay, that's interesting.
Yeah. Okay, that's interesting. Okay, cool. So now we move on to sum extensivity. Okay, so what I didn't mention earlier was that sort of the starting question that we asked ourselves in this project was, so we've got this like equivalence, these two equivalent notions of extensivity, one defined by this equivalence of a functor, well, this functor being an equivalence, and the other one with this pullback coproduct condition that we can impose. And we asked ourselves like, how can this result generalize to the context of sum structures? So this is an answer. I think there are probably multiple answers to this question. Or at least I'm going to work towards an answer. So if we have any objects, x1 and x2, in a category with a sum structure, where all inclusions are C reflecting, so we require that, then we still have that like my monoidal sum induces a functor from, these are supposed to be fancy C's, induces a canonical functor from the comma category over x1 times comma category over x2 to the comma category over the sum, in the same way as what like coproduct does. It's all the same. And yeah, we denote by the following the full subcategory of the comma category over the sum for the fixed x1 and x2, all all C-reflecting morphisms into X1 and X2. So the objects over here are C-reflecting morphisms into the sum of X1 and X2. Okay, so now I will ask you to consider the following conditions on sum, and these will sort of correspond to the requirement that this thing needs to be an equivalence. It's not requiring that it's actually an equivalence, but it's analogous to this bifunctor being an equivalence. Okay, well, the induced functor being an equivalence. Okay, so over here, all this says really is that, like, if I have any C-reflecting F coming into my sum, then I need to find some, I need to be able to find some F1 and F2, F1 going into X1, F2 going into X2, such that their sum is isomorphic to my F. So I just need to be able to pick something such that the sum is isomorphic to any C-reflecting F. And this kind of corresponds to essential surjectivity for C-reflecting morphisms. So we require essential surjectivity for C-reflecting morphisms. And then we have this condition that kind of requires full faithfulness, but not for everything, just when my latter sum is C-reflecting. So then I have this full faithfulness condition satisfied over here. Okay, so those are two conditions. And it turns out that these two conditions hold for a sum structure if and only if the following. So for any diagram of this form, we have that if C-reflecting means, well, implies that these two squares are pullbacks if and only if the top row is isomorphic to a sum diagram. So kind of like what we had for extensivity, but just for C-reflecting morphisms. And then the other part as well. So we require that pullbacks of C-reflecting morphisms along some inclusions exist. And we also require that all inclusions are C-reflecting. Okay, so we define an extensive category to be any category that satisfies like either L star, L star star, either L star and L star star, or G star and G star star. Okay, cool. So why did we require that inclusions are C-reflecting? So there's an example of something that would be sum extensive if we didn't, but isn't very nicely behaved. So that's the monoidal pre-order maybe on the natural numbers. So here we have like objects are natural numbers. For each natural number, there's an object. Morphisms are like the pre-order structure on the natural numbers. So there's a morphism if and only if a natural number is less than or equal to another natural number. And then like we impose a monoidal sum on this, which is just sum of natural numbers. Okay, and then in this sum structure, we have that, so it turns out that this is a sum structure, and we have that like some n less than or equal to p covers some other m less than or equal to p if and only if the sum of m and p and m and n are less than or equal to p. So maybe pictorially we have the following. So if we have that like p is larger than or equal to n and p is larger than or equal to n, then we have that like this morphism covers this morphism if and only if we have that p is larger than or equal to n plus n as well. Okay, and it turns out that only the identity morphisms here are C-reflecting. So that's a very strong condition for this category. And because so few things satisfy the condition of being C-reflecting, we have that this thing turns out to be sum extensive, almost trivially. Well, we would have that it would be sum extensive if we didn't require that inclusions are C-reflecting. So the inclusions are not C-reflecting here, obviously, if they're not always identity. Okay, and this doesn't behave very well, this example. Like most of the results that we'll be discussing in the next section don't hold for this example. Okay, yeah. Cool, so let's look at these results. The definition of disjointness is pretty much the same as for extensivity. So if I have some structure and I have pullbacks along inclusions, then we say that that structure is disjoint if inclusions are monic and pullbacks of inclusions are initial. Same picture, that's redundant again. Okay, and if we have that a sum structure is extensive, then it's disjoint. That one adapts straightforwardly. Cool, and here we say that an initial object is strict with respect to a sum structure if any C-reflecting arrow into it is an isomorphism. So we're not having that any arrow into it is an isomorphism. And if a sum is extensive, then initials are strict with respect to that sum. So I will mention here that we have examples of pointed sum extensive categories, and we can't have that all initials are strict with respect to all morphisms in a pointed sum extensive category, otherwise it would trivialize. So this is why we require C-reflecting. Okay, and then analogously, we say that a sum diagram of this form is universal if putting it back along any C-reflecting morphism into my sum gives us a sum diagram again upstairs. And then we get kind of the same result as we do for extensivity. So we have that a category of a sum structure, C-reflecting inclusions and pullbacks along inclusions is sum extensive or extensive with respect to that sum structure if and only if that sum is universal and disjoint. Nice. Okay, and then I'll also mention a bit on equivalence of sum structures. So if I have some sum structure on a category C and another sum structure on category B, and maybe I have an equivalence of categories between C and B, then we call that thing an equivalence of sum structures if it preserves the sum structure. And we require this to be an isomorphism of sums, so like making the inclusion diagrams commute, triangles. Okay, and these are very nice. I mean, as you can imagine, everything kind of carries over with an equivalence of sum structures. So we have that G covers F if and only if the image of G covers the image of F under our equivalence. We have that F is C-reflecting if and only if the image of F under our equivalence is C-reflecting. And we have that our original sum is extensive if and only if our target sum, our transported sum is extensive.
So what do you mean by this isomorphism thing between this? Is it just any natural isomorphism, or
one that makes the diagram commute with inclusions? So
okay, I see.
Okay, so we have triangles with.
Okay, so there's just is it just a unique thing if it exists then, or?
I believe so. Yeah. Okay. Cool. Cool. So let's take a look at some examples.
I think it's because those things are joint anymore.
Yeah.
Okay. So take rela to be the category with objects, pairs, sets, and the binary relation on that set, and morphisms, the relation preserving functions. Then we can define a monoidal structure on rela as follows. So we take the disjoint union of underlying sets, and we take a relation on that thing to be defined as follows. So we keep the relation for the bottom relation, and we keep the relation for the top relation, and then we require that everything in the bottom is related to everything in the top.
Why is it called rela? Why is it not just rel?
I don't want to confuse it with a category that has morphisms relations.
Okay.
That's usually called rel.
What does SA stand for?
SA.
A in rela. What does A stand for?
Just
a relation. I added one more letter. Okay. Cool. And then it turns out that the C-reflecting morphisms here, I will show you a picture for this situation in a bit. No, it's maybe not nice to look at the condition algebraically. C-reflecting morphisms turn out to be the relation-reflecting morphisms for this sum structure. So this is a sum structure. And it turns out that this sum structure is extensive. Okay, so what's the picture that's happening here? So say I have two sets with relations on them. Then I take the disjoint union of those two to make the sum, and then I keep the relational structure for the top one and the bottom one, and then I require that everything in the bottom is related to everything in the top. And then if I have maybe two relation preserving functions to a common codomain B, so the image here is blue and green, then I'll have that G covers F. Here, if and only if everything in the image of F is related to everything in the image of G. Then I'll have a morphism, a relation-preserving morphism from the sum down to B, making the triangle smooth. Okay, cool. So it turns out that any full subcategory of radar with the 1-point set and reflexive antisymmetric reflection on that, and where objects are reflexive and antisymmetric, then the C reflecting morphisms are mono. So it's not that like they are exactly the monomorphisms. It's not even that they're exactly the relation preserving monomorphisms, or the relation reflecting monomorphisms, sorry, but they are all mono when this holds. Okay, and many examples like this are in fact sum-extensive. So pre-orders, if I take objects to be pre-orders or partial orders, or direct complete partial orders, and I think this holds if you still only consider morphisms to be Scott continuous. Nice.
So you told us earlier that geometric categories end up being extensive. Is pre-orders extensive still for the usual coproduct?
Yes.
I think so.
Yeah, it is. For the same reason, I mean, like topological spaces are extensive, right?
Right.
Pre-orders.
Right.
Like
okay. Yeah. I believe it.
Yeah.
Alexandral spaces. Yeah. Okay. And do we
It's
still...
worth pointing out that some of these are examples of both.
Of both, yeah. So the,
I mean, the sum here is different.
The sum is different from coproduct. Yeah. Yeah. Okay. And then if we just have countably complete partial orders, it still works out. Chains with like total orders, and then the simplicial categories, like finite total orders.
Yeah, but morphisms are relations in all these, or not?
Relation preserving function.
Right.
Okay. So, yeah, I don't know whether it is.
No, it's still relation preserving. It's monoidal pre-orders.
Oh, okay.
So morphisms are still usually
Relation.
The category of chains, for example, that wouldn't have. Would it have coproducts? Probably not.
No, I don't think so.
So it's important to distinguish which of these examples
yes.
are no longer extensive, but still some extensive.
Okay, so certainly with chains and simplicial category, we don't have coproducts anymore, but we do have this sum extensive sum structure.
Wait, with simplicial category, do we not have coproducts?
No, again, they change, right?
Oh, right, yes, sorry.
Yeah, they're kind of the same example, I guess. Okay, so unfortunately, we don't get examples of this when we consider like bounded relations. So, for example, complete Hating algebras or domains. The problem here is that we lose being a sum structure because we don't have like a empty initial object. So it's no longer the monoidal unit of our sum structure. That said, for any domain theorists sitting in the audience, I'd be very curious to know like what the interpretation of the stacking operation would be in domain theory. So if you guys like have thoughts about that, please do share at some point.
So maybe it's also useful to remark that this from delta, which also can be seen as the category of ordinal numbers, we can actually extend it to all ordinals.
Right.
The sum for which it is extensive is the usual addition of ordinal numbers.
Yes.
So the operation is a useful operation. It's the addition of ordinal numbers. While there is no coproduct, the usual addition of ordinals now becomes a monoidal structure, which is not a coproduct.
But it's still no coproduct at all. Yeah, but it's still sum extensive. Yeah. Okay. I haven't thought of that one either. Thank you. Okay, cool. So let's try and transport one of these examples. Cool. So for any pre-order, we can associate it to a topology. So the specialization topology would be one with the same underlying set, but then the opens are the up-close sets with respect to our pre-order. And then it turns out that this assignment, so here like functions just go to the underlying, the same function, the same underlying function, and it turns out to be continuous. This is a well-known equivalence of categories between preorders and Alexandrov topological spaces. So those are just where you have like arbitrary intersection of opens are still open. Cool. And it turns out that this thing also gives an equivalence of some structures. Well, maybe it doesn't turn out. It does give an equivalence of some structures. So this is always a construction that you can do. You can like take a sum structure and an equivalence and then transport it over to a sum structure in the other category.
What is the sum for topological space, for Alexander space?
I'm going to do that now. But you could always transport a sum structure along an equivalent over, and it will give you an equivalent sum structure. Okay, so what is the sum structure on spaces? So we have underlying set the disjoint union as usual, I guess, and then opens are of the following form. So we have like all opens of our top space as usual, and then we have opens of our bottom space union everything in the top. Okay. And it turns out that like this doesn't just work for Alexandrov spaces. This is also some extensive sum structure for all topological spaces, which is a bit weird. I thought the proof was simple, but then I found mistakes. And it wasn't so simple. Okay, cool. So like pictorially, maybe we just try and visualize what's going on with covering over here. So if we have space x and y, and we take their sum, struggle to illustrate what's going on with the opens over there, but then we have like morphisms f and g to some common codomain, that's orange. Then we have that like g covers f, if and only if, for any open in my space downstairs, if that meets f, so has non-intersection with the image of f, then it like eats the entire image of G. So it can't see the image of G anymore. And if this holds, then G covers F, if and only F. Okay, cool. Another example is that of injections outside the kernel of pointed sets. So take P to be the wide subcategory of the category of pointed sets with morphisms just injections outside the kernel. So that's like, you can have any kind of kernel, but the stuff outside the kernel needs to be mapped injectively to the target. So if we take sum over here to be the usual coproduct of pointed sets, then we obtain a sum structure that's not coproduct. And it turns out that this thing is pointed. Do I not say that over here? Anyway, it turns out that this thing is pointed, which is quite remarkable because pointedness trivializes for like extensivity of coproducts. Okay, cool. So what's the picture over here? So if I have like a pointed set with fixed point x and a pointed set with fixed point y, their sum is just going to retain each, so like be the disjoint union of these two, but we're going to glue the 2 points together. And then we'll have that maybe like 2 injections outside the kernel, where to some common codomain. Then we have that G covers F, if and only if we have that the image of G outside the kernel doesn't have anything to do, so it's disjoint from the image of F outside the kernel. Yeah.
So you could probably phrase this whole example in terms of like sets with partial functions.
It's covering. Okay. Cool. So that's what I said. And then it turns out that the C-reflecting morphisms here are exactly the monomorphisms.
I think that actually this partial function way of thinking about pointed sets may be more useful because we encounter a lot of partial functions in applications of mathematics, especially calculus.
Yeah.
When we do things in a category theoretic way, we always say partial functions are bad. But actually, they're not bad because the category of sets with partial functions is the category of pointed sets. So they're actually quite good.
Yeah, and like computer scientists like working with partial functions, I think. No? Okay, there we go. And it turns out that this category is sum-extensive and pointed. And yeah, this is remarkable because pointedness trivializes for usual extensivity. Okay, so now we can transport this. So for any pointed set, take its image under E to have the same underlying set, but we remove the point. And And then for a morphism of pointed sets, we take its image under E to be a partial function, where the domain of definition of my image under E of F is everything in the domain of F without the kernel of F. So it's only defined for things outside the kernel, and then it has the same opinion as F does on all of those things. So you can maybe think of like the points as like a rubbish bin, and then you send everything outside in the kernel to the rubbish bin. Okay, so this is a well-known equivalence of categories between pointed sets and partial functions. And then it turns out that like this equivalence restricted to P gives us the category of injective partial functions. So this is nice because like monomorphisms of partial functions are interesting because they have to be like, they have to have total domain of definition. So on the pointed set side of things, they need to have like zero kernel. So this is kind of a more encompassing notion than just monomorphisms of partial functions. Okay, cool. The last thing I want to talk about is M restrictions. So what is an M restriction? So for any category C, we take M to be some class of morphisms satisfying a list of conditions. So M needs to have all identity morphisms and needs to be closed under composition. It needs to be closed under sums of morphisms. It needs to have all the sum inclusions. We need to have that pullbacks of morphisms in M along sum inclusions exist. And if I pull back, then it's still going to be an M. And if I have morphisms F and G, and I have that the composite FG is an M, then G needs to be an M as well. Each morphism in M needs to be C reflecting. So these are like monomorphism-like morphisms, I guess. Anyway, we define the M restriction of a category C to be the wide subcategory of C with morphisms in M. Okay, so it turns out that if we start out with any sum-extensive category, then any M restriction of that is also sum-extensive. So this gives us like a nice mechanism to derive a host of examples of sum-extensive categories which are not extensive. So for example, if we take M to be like monomorphisms, then we're always going to get a valid M restriction. In particular, if we take just like sum to be coproduct of sets and M to be the injections, then we get an interesting sum structure that isn't coproduct. And yeah, M restrictions tend to be examples where all morphisms are C reflecting, but we don't have that the sum structure is coproduct. So it doesn't necessarily have to be the case. If everything's C reflecting, you get coproduct. Okay, so here's something introduced by Emma Tiat and Michael Hufnagel last year. So if we have any morphism in a category, we say that the morphism is extensive if pulling it back along coproducts, or we can pull it back along coproduct inclusions. And for any diagram of the following form, where the bottom row is a coproduct, we have that the top row is a coproduct if and only if the left and right squares are pullbacks. So like the extensivity condition needs to hold for our morphism, just our morphism. Okay. Then we say that for a class of morphisms M, a category is M extensive if all morphisms in that class are extensive. Also due to Michael. Okay, so it turns out that if we have that M restriction of a category is sum extensive, then C is extensive. The category is M extensive, sorry. This is the case for coproducts. So where your sum structure is coproduct. Okay, cool. That's everything that I had to share. Thank you. Anybody have any questions?
Okay,
yes.
So can you just remind me how the cover relations are related to the kind of sum extensivity that you had?
So it goes via the monoidal structure. So there's like a one-to-one correspondence between cover relations satisfying some criteria and monoidal structures where like initial is unit and we have
Okay,
disjoint epimorphic.
Right, okay, so, but yeah, so then I assume Grothendieck topologies are cover relations as well, right?
I think so, yeah.
And so, yeah, is there any relationship between, if you have a Grothendieck topology and you take the subtopos corresponding to that, and then you kind of look at what you maybe get, the sum like extensive thing. Is there any way to relate basically the Grothendieck topology and what it generates with what you do with the cover relation? Or
I think the class of cover relations that like Grothendieck topologies form a part of is like a different class from those that give us some structures, monoidal structures.
Oh, okay.
Yeah, so in the paper where I introduced cover relations, I looked at two classes. One is that arise from factorization systems. The Grothendieck topology one is very similar to that.
Okay.
And ones that arise from monoidal categories. And if you intersect them, you get almost nothing.
Okay.
Very divergent
I see.
classes.
It would be nice to unify.
So one of the property, for instance, so there are properties that are typical to one class and very atypical to the other one. For example, transitivity is a property that's very typical to one class.
Yes.
Very atypical here.
Okay.
And here, on the other hand, symmetry is a very typical property, like for groups, images commute.
Yes. Yes.
Whereas there is very, very much atypical property.
But we don't need symmetry for a sound structure.
Yeah, that's true.
It's not so like the stacking of spaces.
When I think the monoidal structure is symmetric, I think that's going to be symmetric.
Yeah, that makes sense.
Yeah, I imagine. And the symmetry is probably like uniquely determined in some way, right? Also. Yeah.
Yeah.
Yeah, for these monoidal categories, coherence conditions automatically hold because of the joint part.
If
you want to try and generalize your pointed sets example, I guess your morphisms are composites of normal epimorphisms and monomorphisms.
I think
In your category of pointed sets, they're composites of normal epis and monos. Is
think-
what you take it as your morphisms.
I think I tried that, or at least I think I like formulated a different generalization, and then it turned out not to be equivalent to that. So there are multiple options.
Maybe the other things work. I'm just saying that's one way of viewing what you've done.
Probably more natural than what I came up with. But yeah, that's still an active part of this project. Okay. Does anybody online have any questions?
I wanted to ask, is there a version of extensivity for general colimits rather than coproducts? Like something similar to that theory?
That's an interesting question.
Well, yeah, that's kind of what I was saying earlier. So there's this notion of like a Van Kampen colimit.
Yeah.
Right.
Which is like trying to generalize this from like just coproducts to more general colimits. But and I think if you do it for like the version you get for kind of co-equalizers and things ends up being related to exactness. But if you want it for all colimits, you can't get it in a one category. You have to have like an infinity category or something in order for you to get all colimits to be Van Kampen.
I see. Yeah, it's true. Van Kampen colimits are a sort of the thing I was asking about.
Okay. Yeah, I mean, I guess like you could do like universality for arbitrary colimits. Maybe the question is if you could do disjointness for arbitrary colimits and whether that will give you an interesting notion of extensivity for arbitrary colimits. It's a question. Okay. Yes.
Sorry, one more question. I might have missed this because I walked in late. But what was your motivation for wanting to look at some
structures? Yeah, so the original question was we have this like these two equivalent definitions of extensivity. So the one using an equivalence of functors and the other using like pullbacks, if and only if coproduct on a specific kind of diagram. And we want to generalize this theorem to the context of some structures. So we have an answer.
But why some structures in particular?
Oh, I guess like some structures are sort of like coproduct, but substantially more general. So you can sort of apply the tools of extensivity. I mean, like a lot of results generalize from the context of just plain extensivity to the context of some structures, and you can use all of that apparatus to treat a whole bunch of new examples. Yeah.
There seems to be a message in chat.
Oh.
That's worth reading.
I should read.
Oh.
Oh, I think that was at the beginning. Okay. Cool. And thank you so much for listening.
Thank you.